Welcome back to another explainer. Today we're diving into a forensic investigation of the digital maps we use literally every single day, and the inherent mathematical flaws hiding just beneath their surfaces. We trust spatial data implicitly. We use it to route emergency vehicles, manage global supply chains, or just to figure out the fastest way to get our morning coffee. But beneath that super smooth interface on your phone lies a pretty fascinating secret. A minor, completely invisible calculation error buried deep in a dataset. Well, that could mean a delivery truck getting routed to a dead end instead of a major highway. The digital environments we trust so deeply just aren't perfect reflections of the real world. They're carefully calculated models balancing on this foundation of acceptable, managed uncertainty.
There's this fantastic piece of dry humor, allegedly from Winston Churchill, that goes, "The only maps you can trust are those you falsified yourself." And honestly, it perfectly captures the reality of cartography. Every single map is a product of selections, aggregations, and classifications. When you really think about it, taking the incredibly complex, messy, three-dimensional sphere of the Earth and squashing it down into two-dimensional data inherently demands massive compromise. You simply can't compress reality into a data set without losing some information along the way. So understanding exactly what gets lost and how much it actually matters is what we're decoding today.
All right, so here is our agenda for today. We've got 5 key areas to cover. First, the myth of perfect maps. Second, defining geospatial uncertainty. Third, hunting for ground truth. Fourth, gross, systematic, and random errors. And fifth, cardinal and categorical errors. Let's get right into it.
Starting off with Section 1, the myth of perfect maps. Shifting from absolute perfection to mathematical reality.
Moving right along to Section 2, defining geospatial uncertainty, navigating ISO standards.
So, since we know absolute perfection is mathematically impossible, how do cartographers actually measure a map's worth? Well, the international community sets the baseline using the ISO 8402 standard for quality. It officially defines quality as the totality of all properties of geodata that are necessary to meet certain requirements of an application. Now, in the geospatial industry, this is commonly known as fitness for use. And this is a massive paradigm shift. Quality isn't about having 0 errors. Quality means asking, is this data accurate enough for your specific real-world need? Think of it this way. If you're mapping a commercial airline flight path, you absolutely need extreme sub-meter precision to ensure safety, right? But if a video game developer is using city data to build a virtual background, they really just need the general shape of the city blocks. The exact same dataset might be completely unfit for the pilot, but absolutely perfect for the developer. Now, when we look at the overarching concept of uncertainty, it broadly splits into 2 distinct branches. You have the properties we can actually measure and quantify, and then you have the tricky, non-measurable properties. And we really have to account for both sides of this if we want to truly understand how reliable our geographic data is.
So, the measurable properties are the hard data. These are the math problems. This includes things like positional accuracy, which basically asks, is the object truly where we say it is? It also includes temporal accuracy, making sure the timing of the data is correct. But that other branch, the non-measurable properties, those are qualitative doubts. They're fundamentally human judgment problems. For instance, imagine throwing a pixelated 100-meter checkerboard raster grid over a highly detailed winding little creek. The grid itself might be perfectly calculated, but the model is just entirely unsuitable for studying the subtle curves of the water. You can't easily slap a hard mathematical number on that kind of conceptual mismatch, but it severely impacts the map's fitness for use.
Which brings us to Section 3, hunting for ground truth, establishing a baseline.
If we're going to catch the mathematical errors in our measurable data, we need a really reliable suspect to compare them against. Because if you want to figure out how wrong a map is, you first kind of need to know what right looks like. In geospatial data, absolute truth doesn't really exist, so we rely on what's called ground truth. Ground truth consists of as perfect as possible baseline samples taken from a significantly higher quality measurement class. Let's say you have a map generated from standard satellite imagery. To find its errors, you'd send a surveyor physically out into the field with a highly accurate professional-grade GPS receiver to take exact physical coordinates. Those highly accurate points become your relative ground truth.
But obviously, you can't manually measure the entire world with professional-grade GPS equipment. That would take decades and bankrupt literally any project. So, finding this truth requires really careful sampling. Cartographers have to balance 2 main factors here. First, the number of samples, like how many data points can a project actually afford based on budgets or statistical targets. Second, the spatial distribution. How are we scattering these points across the map? Do we just place them randomly? Do we use a systematic grid? Or do we use a stratified approach? Stratification is absolutely crucial, because if you only sample randomly, you might accidentally gather all your points in wide flat plains and completely miss the complex data errors hiding out in a dense mountain range or a deep urban canyon. You have to make sure every single geographic region is properly represented.
All right, into Section 4, gross, systematic, and random, the three main suspects of geospatial error.
I always like to think of geospatial error as kind of like an archery target. A gross error is just a massive outlier. It's like an archer shooting an arrow into the completely wrong target. This happens when someone accidentally types a 9 instead of a 1, or a sensor briefly glitches out. It's just wildly off the mark. Systematic errors, though, are a bit different. Imagine the archer shoots 5 arrows and they form this perfectly tight grouping, but they're all clustered in the top right corner, way far away from the bullseye. That's a systematic error. It represents a constant offset, usually caused by equipment that just wasn't calibrated correctly to 0. It has fantastic precision, but terrible correctness. And finally, random errors. This is when the arrows are scattered loosely all around the true bullseye. This affects precision, and it's usually caused by tiny, unpredictable variations, maybe changing weather conditions or slight atmospheric interference during a measurement.
And lastly, Section 5, cardinal and categorical errors, calculating the mess mathematically.
When we're evaluating cardinal data, which is just a fancy way of saying quantitative numbers that we can actually do math on, like height, speed, or distance, anomalies are relatively easy to spot. Imagine you're reviewing a data set of height measurements compared against a known ground truth of 10 meters. If you scan down the measurement column, notice that massive 32-meter measurement logged right there at point 4. That jumps right out at you. That is a textbook gross error. And before any kind of complex statistical analysis can even begin, cartographers have to address giant anomalies just like that one.
So, to clean up cardinal metric data, cartographers follow a very strict sequential 3-step procedure, and the order here is incredibly important. First, we must eliminate the gross errors. We completely toss out that massive 32-meter typo. Why? Because if we leave it in, it'll completely warp the average of the entire dataset, ruining our ability to find any subtle trends. Second, with the outliers gone, we identify the systematic errors. We calculate the mean deviation of the remaining points, and if there's a constant additive offset, like, say, all the points being exactly 2 meters too high, we mathematically shift all the data points back to 0. Third, and finally, we determine the random errors by calculating the standard deviation. This tells us the precision, showing exactly how much random scatter is still left over after the gross and systematic errors have been successfully neutralized.
Now, everything we just went over works perfectly for numbers. But what happens when the map isn't tracking numbers at all, but instead tracks nominal classes like forest, water, or city? This is categorical data, and you obviously can't calculate the mathematical average between a forest and a city. It simply doesn't make any sense. So to find uncertainty in categorical data, cartographers use an entirely different tool called an error matrix. Think of it like a highly detailed scorecard. It tracks 2 really vital metrics, producer's accuracy and user's accuracy. Producer's accuracy looks at things from the map maker's perspective. Basically, how often did the map correctly label a forest when the raw satellite imagery actually showed a forest? User's accuracy, on the other hand, looks at reality on the ground. If you, the user, walk to a location marked forest on your map, how often do you actually find trees rather than a recently paved parking lot? The matrix tracks all of these matches and mismatches to score the data's reliability without ever needing to calculate an impossible mean.
At the end of the day, maps just aren't perfect mirrors of reality. They are carefully managed, mathematical models of probability, and their true quality is ultimately judged entirely by their fitness for use. So the next time your phone's routing app navigates you perfectly to an unfamiliar destination, avoiding traffic and shaving minutes off your commute, I really want you to ask yourself, how much carefully calculated uncertainty is silently hiding inside the screen you're holding right now? Thanks so much for joining me on this deep dive. Keep questioning the data, and we'll see you on the next explainer.